specific problem that utilizes the absolute sign so we get a better understanding of it is 4 plus 5i minus 7, and the modulus of it is equal to 3. Find the center of the circle and the radius. So I said there is no requirement for z to have a minus 1 coefficient, and so this should be removed. So this is what I do. I notice how there's a minus z in here just floating around, but we know that the equation is z minus z1. There is no minus in front of the z. So I bring it forth and I factorize out minus from all of them such that it stays legit factorization. The absolute value of minus 1, so if you consider that I can allow for an absolute sign in here, and therefore I would be taking the absolute value of minus 1, which is just 1, and 1 times anything just leaves this completely out. So I would have this instead. Instead, what I would have is just this part here, z minus 4 minus 5i equals 3. According to our circumstances from before, if you can recall, I factorized out the minus sign in order to find the center point, in order to stick to the equation that we have. So what I'm going to do is the same here. If factorize out minus 1, I would be left with 4 plus 5i. Therefore, the center point is 4, 5, real value 4. That is to say, it would probably be, if we suggested that that was 2, it would be here at a 4, and an imaginary value 5, which we would perhaps say is there. So the center point would be something like that, there. And then we'd have a circle of radius what? The circle will be of radius 3. Okay, now what we're going to now look at is a way in which we can show that this argument here, the argument of z minus z1 equals r, why that is true. That's what we're going to look at next. How do we add argument to this truly being a circle? And all I'm going to do is I'm going to suggest that we know that we can write z as x plus iy. That is, we can consider this real as x in there, and we consider this imaginary plane as y. So given that it is imaginary, we say x plus iy represents any value of z, or represents z completely. And you can do, and the similar situation we've discussed in past videos is a plus ib or bi. There's another way of writing a vector, or not vector, a vector-esque a value in the complex plane z1. And we're going to implement these two into our equation. This leads us quite nicely into taking z minus z1, so that is to say that this is z minus z1. Let's put a little subscript 1 in there to keep us aware of that concept. Z minus z1 equals r, and therefore I've substituted x plus iy in here, a plus bi in there, and then I can collect real and imaginary terms. That is real. This is real, so this z x minus a is in the real part. The minus iy, sorry, a tongue twister there, iy, or perhaps not, bi, they are both imaginary. And this is a minus, so if I factorize out that minus, multiply out this minus, I'll end up with y minus b in the imaginary. So I'm left with this. However, the absolute signs represent trying to find the length. So say, for example, you've got a real plane that looks like that. You have an imaginary plane that looks like this, and you have a circumstance where this represents some sort of value on that plane, some sort of position on that plane, let's say that point here. If I then were to say, well, what is the length from the origin to that position, we can very quickly conclude that you could work that out quite comfortably by using Pythagoras' theorem, in that the real part, x minus a, would need to be squared. So the real part here, x minus a, there would be squared. And the imaginary part, y minus b, will be squared also. Therefore, I can say, using Pythagoras' theorem, a squared plus b squared equals c squared, with the square root to get rid of the squared. I can do the same to get the length of the radius in these circumstances. And therefore, if I square both sides, you can see there you have it. You have additional argument that z minus z1 absolute equals r is the same as, it represents a circle in the complex plane, as when you utilize values from what we are more familiar with in the Cartesian plane, like x and y, a constant A, a constant B, we end up with what could be described as a equation for a circle.